A neutrino is a lepton, an elementary particle with half-integer spin, that interacts via only the weak subatomic force and gravity. The mass of the neutrino is tiny compared to other subatomic particles. They are the only identified candidate for dark matter, specifically hot dark matter. Neutrinos come in three flavors: electron neutrinos, muon neutrinos, and tau neutrinos. Each flavor is also associated with an antiparticle, called an antineutrino, which also has no electric charge and half-integer spin. Neutrinos are produced in a way that conserves lepton number, i.e., for every electron neutrino produced, a positron is produced. And for every electron antineutrino produced, an electron is produced as well. Neutrinos, named as such because they are electrically neutral, are leptons, and so are not affected by the strong force either. The weak force is a very short-range interaction, and gravity is extremely weak on the subatomic scale. Thus, neutrinos typically pass through normal matter unimpeded and undetected. Neutrinos can be created in several ways, including in certain types of radioactive decay, in nuclear reactions such as those that take place in the Sun, in nuclear reactors, when cosmic rays hit atoms, and in supernovae. The majority of neutrinos in the vicinity of the Earth are from nuclear reactions in the Sun. In fact, about 65 billion solar neutrinos per second pass through every square centimeter perpendicular to the direction of the Sun in the region of the Earth. Neutrinos oscillate between different flavors in flight. That is, an electron neutrino produced in a beta decay reaction may arrive in a detector as a muon or tau neutrino. This oscillation requires that the different neutrino flavors have different masses, although these masses have been shown to be tiny. From cosmological measurements, it has been calculated that the sum of the three neutrino masses must be less than 1/millionth that of the electron. History. Paulie's proposal. The neutrino was postulated first by Wolfgang Pauli in 1930 to explain how beta decay could conserve energy, momentum, and angular momentum. In contrast to Niels Bohr, who proposed a statistical version of the conservation laws to explain the event, Paulie hypothesized an undetected particle that he called a neutron, in keeping with convention employed for naming both the proton and the electron, which in 1930 were known to be respective products for alpha and beta decay. He considered that the new particle was emitted from the nucleus together with the electron or beta particle in the process of beta decay. James Chadwick discovered a much more massive nuclear particle in 1932 and also named it a neutron, leaving two kinds of particles with the same name. Paulie earlier had used the term neutron for both the particle that conserved energy in beta decay, and a presumed neutral particle in the nucleus. The word neutrino entered the international vocabulary through Enrico Fermi, who used it during a conference in Paris in July 1932 and at the Solvay conference in October 1933, where also Paulie employed it. The name was jokingly coined by Edoardo Amaldi during a conversation with Fermi at the Institute of Physics of Via Panisperna in Rome, in order to distinguish this light-neutral particle from Chadwick's neutron. In Fermi's theory of beta decay, Chadwick's large neutral particle can decay to a proton, electron, and the smaller neutral particle, N0p++ E- Nui. Fermi's paper, written in 1934, unified Paulie's neutrino with Paul Dirac's positron and Werner Heisenberg's neutron-proton model and gave a solid theoretical basis for future experimental work. However, the journal Nature rejected Fermi's paper, saying that the theory was too remote from reality. He submitted the paper to an Italian journal, which accepted it, but the general lack of interest in his theory at that early date caused him to switch to experimental physics. Nevertheless, even in 1934 there were hints that Bohr's idea that the energy conservation laws were not followed was incorrect. At the Solvay Conference of 1934, the first measurements of the energy spectra of beta decay were reported, and these spectra were found to impose a strict limit on the energy of electrons from each type of beta decay. Such a limit was not expected if the conservation of energy was not upheld, in which case any amount of energy would be expected to be statistically available in at least a few decays. The natural explanation of the beta decay spectrum as first measured in 1934 was that only a limited amount of energy was available, and a new particle was sometimes taking a varying fraction of this limited energy, leaving the rest for the beta particle. Paulie made use of the occasion to publicly emphasize that the still undetected neutrino must be an actual particle. Direct detection. In 1942, Wang and Chang first proposed the use of beta capture to experimentally detect neutrinos. In the 20th of July 1956 issue of Science, Clyde Cowan, Frederick Rain, B. Harrison, W. Cruz, and A. in this experiment, now known as the Cowan-Rain neutrino experiment, antineutrinos created in a nuclear reactor by beta decay reacted with protons to produce neutrons and positrons. Nu E plus P plus N0 plus E plus. The positron quickly finds an electron, and they annihilate each other. The two resulting gamma rays are detectable. The neutron can be detected by its capture on an appropriate nucleus, releasing a gamma ray. The coincidence of both events, positron annihilation and neutron capture, gives a unique signature of an antineutrino interaction. Neutrino flavor. The antineutrino discovered by Cowan and Rain is the antiparticle of the electron neutrino. In 1962, Leon M. Lederman, Melvin Schwartz and Jack Steinberger showed that more than one type of neutrino exists by first detecting interactions of the muon neutrino, which earned them the 1988 Nobel Prize in Physics. When the third type of lepton, the tau, was discovered in 1975 at the Stanford Linear Accelerator Center, it too was expected to have an associated neutrino. First evidence for this third neutrino type came from the observation of missing energy and momentum in tau decays analogous to the beta decay, leading to the discovery of the electron neutrino. The first detection of tau neutrino interactions was announced in summer of 2000 by the donut collaboration at Fermi Lab. Its existence had already been inferred by both theoretical consistency and experimental data from the Large Electron-Positron Collider solar neutrino problem starting in the late 1960s. Several experiments found that the number of electron neutrinos arriving from the Sun was between 1/3 and 1/2 the number predicted by the Standard Solar Model. This discrepancy, which became known as the solar neutrino problem, remained unresolved for some 30 years. It was resolved by discovery of neutrino oscillation and mass oscillation. A practical method for investigating neutrino oscillations was first suggested by Bruno Pontecorvo in 1957 using an analogy with kaon oscillations. Over the subsequent 10 years he developed the mathematical formalism and the modern formulation of vacuum oscillations. In 1985, Stanislav Mohav and Alexei Smirnov noted that flavor oscillations can be modified when neutrinos propagate through matter. This so-called Mohav-Smirnov-Wolfenstein effect is important to understand because many neutrinos emitted by fusion in the Sun pass through the dense matter in the solar core on their way to detectors on Earth. Starting in 1998, experiments began to show that solar and atmospheric neutrinos change flavors. This resolved the solar neutrino problem. The electron neutrinos produced in the Sun had partly changed into other flavors which the experiments could not detect. Although individual experiments, such as the set of solar neutrino experiments, are consistent with non-oscillatory mechanisms of neutrino flavor conversion, taken altogether, neutrino experiments imply the existence of neutrino oscillations. Especially relevant in this context are the reactor experiment CAMLAND and the accelerator experiments such as -. The CAMLAND experiment has indeed identified oscillations as the neutrino flavor conversion mechanism involved in the solar electron neutrinos. Similarly, - confirms the oscillation of atmospheric neutrinos and gives a better determination of the mass-squared splitting. Takaraki Kahita of Japan and Arthur B. MacDonald of Canada received the 2015 Nobel Prize for Physics for their landmark finding, theoretical and experimental, that neutrinos can change flavors. Supernova neutrinos. Raymond Davis, Jr., and Masatoshi Koshiba were jointly awarded the 2002 Nobel Prize in Physics, Davis for his pioneer work on cosmic neutrinos and Koshiba for the first real-time observation of supernova neutrinos, the detection of solar neutrinos, and of neutrinos of the SN 1987A supernova in 1987 marks the beginning of neutrino astronomy. In an average supernova, approximately 1057 neutrinos are released.